In question 6, ammonia is a weak alkali. Consider the following equilibrium that exists: an aqueous solution of ammonia. Ammonia plus water gives ammonium ion and a hydroxide. And Kb is called a dissociation constant of a base. And it's the same idea, like we can also have pKb if and Kb. If a higher dissociation means strong base, so the dissociation constant of a base Kb, which is a product divided by reactant. Calculate the concentration of the hydroxide ion at equilibrium when 4 mole per dm cube aqueous ammonia solution. Assume that the concentration of ammonia in equilibrium is 4 and the equilibrium concentration of hydroxide ion is equals to equilibrium concentration of ammonium ion. So it means we need the concentration of the hydroxide ion. So how we can work out the concentration of we just have to solve, like the equation is already given to us. So Kb is there. This is a Kb. So we have Kb. The constant calculate. We have to calculate the concentration. This is unknown. This is what we need. When 4 mole per dm cube aqueous ammonia. So we have aqueous ammonia 4 mole per dm cube. And the concentration of ammonia at equilibrium. So how to do such question? So original concentration of aqueous ammonia was 4 and this was 0 and 0. But at equilibrium, because it's a heterogeneous equilibrium, like this is aqueous, and liquid, that's why when we write the dissociation constant, we did not include water. Water is liquid, rest all of them are aqueous. Heterogeneous equilibrium, we don't include liquid and a solid. So at equilibrium, if this is x, this will be 4 minus x. And because it's a weak base, so we assume that the dissociation x is very small. So 4 minus x is approximately equals to 4. X, like if I say 4 minus 0.000001, so it is approximately equal to 4. So that's why the x is very small. We ignore that. So when we write the formula for Kb, Kb is a product divided by reactant. So concentration of ammonium ion, the concentration of the hydroxide ion, and the concentration of aqueous ammonia. Why we did not include the water? Because water is a liquid and in a heterogeneous equilibrium, we don't include liquid and a solid. We only include aqueous and gases. So Kb is given to us, that is 1.8 into 10 to the power minus 5. This will be x. This will also be x. And here it is 1.8, 4 minus x. But as I mentioned, 4 minus x is approximately equals to 4. So instead of writing 4 minus x, I can write directly 4. And this 4 will be multiplied, x multiplied by x will become x square. So it is 1.8 into 10 to the power minus 5 multiplied by 4 and taking a root. That will give us a value for the concentration of a hydroxide ion, which is 8.4 exponent minus 3. Is it clear how we worked out the concentration of the hydroxide ion? Any doubt in this? Then calculate the pH of 4 mole ammonia solution. So we already have the hydroxide ion concentration. We already have the hydroxide ion concentration. The hydroxide ion concentration, the previous answer, it was 8.4, 8 into 10 to the power negative 3. And we know the concentration of hydrogen ion and the hydroxide ion, that is equals to Kw, which is the dissociation constant of the water. So, which is at 25 degrees centigrade or 298 Kelvin, it is 1 into 10 to the power minus 14. So 1 into 10 to the power minus 14, the hydroxide ion concentration is 4.84 into 10 to the power minus 3. And we can work out the concentration of hydrogen ion. This is multiplied, other side divide. So this will give us the concentration of hydrogen ion in the mixture. That is 1.179 into 10 to the power minus 12. And then to get the pH, we use a formula. The pH is equals to minus log of hydrogen ion concentration. So minus log of hydrogen ion concentration was 1.17 into 10 to the power minus 12. So that will give us 11.9, the pH of this solution. And it is an alkaline solution, a weak alkaline solution. So it is less than 12. Calculate the pH of 4 mole per hydrochloric acid. Now, hydrochloric acid is a strong acid. So what could be the pH of 4 mole per dm cube hydrochloric acid? We have the formula. pH, like if we have a hydrochloric acid, which is a strong acid, so HCl will dissociate into what? H plus ion and Cl minus. And if it is a 4, this is 0 and 0. But at equilibrium, all will break down and there is no molecule left behind. So the concentration of a hydrogen ion is same as the concentration of acid, original concentration. So pH is equals to minus log of hydrogen ion. So we'll just take a minus log of 4. So what is a negative log of 4? Negative log of 4. Which answer for this? .6. Okay. So 0.6. Yeah, minus 0.6. Okay. And the pH scale is given. So for now, what draw a titration curve. As you can see, this is a titration curve. Draw a titration curve shows a change in pH for 4 mole per dm cube hydrochloric acid is added to aqueous ammonia solution. So in the beginning, we have aqueous ammonia. This is an aqueous ammonia. And what was the pH of aqueous ammonia? Original pH, it was 11.9. Okay. Now we want to add a hydrochloric acid, and what is the final pH of hydrochloric acid? That was minus 0.6. The pH of the HCl. This is a weak alkali. So remember, like a weak alkali, what is the range for weak alkali? The vertical section. So it is around 8. 8 or less than 8, you can also say. Like it is less than 8, and it is a strong acid. If it is a strong acid, so the lower section will be around what? It will be around 4. So mean the vertical section is from 4 to 8. And what is the ratio between them? If I write because to know, understand the ratio, you should write the equation between them. So ammonia react with HCl. So it will produce ammonium chloride. So ratio is 1:1. So originally the pH should start with 11.9, somewhat here. And it should end around negative 0.6, somewhat here. And the ratio is 1:1. So if we have a 25 cm cube of alkali, 25 cm cube of acid is needed. So at 25, we'll have a vertical section. At 25, we'll have a vertical section ranges around 4 to 8. Now, look, first, initially, if you see, we have ammonia in the solution and we are adding an acid. So when we add acid, So when not all of the ammonia, aqueous ammonia reacted, so it will have ammonia. And when some HCl will react with ammonia, it will produce ammonium chloride. So it means this will be weak base and a salt. So whenever weak base and a salt is there, so originally the solution will act like a buffer. So when a solution act like a buffer, it will try to resist the change in pH. So in the beginning, we'll have a horizontal line to show, like the moment first we add, there will be a change in pH, then it become horizontal. Why it become horizontal? Which shows the solution is acting like a buffer. And then the pH will change once the amounts are same. And this will till 0.6, it will be like this. So this will be the shape of the graph. Why I drew a horizontal line? Why not a line like this? Why there's a horizontal line in this section which shows that the solution is acting like a buffer, because like when you add some or a small quantity of HCl, so ammonia is more and HCl react with ammonia to produce some ammonium chloride. So there is a salt and a weak alkali, and it's salt. So when we have a weak alkali and salt, the solution will act like a buffer. Is it clear, the shape of this graph? Anyone having a doubt or a question this? Then we have the next part. Select a suitable indicator. So which indicator we can use? So we have this vertical section from 4 to, it was a weak alkali. So 8 to 4, we were having this. So we have to select an indicator which show a color change. We cannot use any of them because this can be used. This can be used. This can be used. This can also be used. This can be used. Best one is what lie between, like 5 to 8 is lying between or under the range. That is the best indicator. 5.2 to 6. So these can be used. This can be used. This cannot be because it's like both are outside. This cannot be. So any of the indicator we can mention, and we can mention a color change first, initially alkaline and then in acidic. Like because originally the solution was alkaline and then it was acidic. The titration above can be used to determine the concentration of ammonia when ammonia is distributed between two immiscible solvents. An experiment is carried out to find the concentration constant of the reaction. 75 cm cube of 4 mole per dm cube aqueous ammonia and 75 cm cube of trichloromethane shaken together. The two liquids are allowed to separate and 25 cm cube of aqueous layer is taken and titrated with 4 mole per dm cube hydrochloric acid, and the whole procedure is repeated. The average titer was 24. Calculate the number of moles of ammonia, hence calculate the concentration in aqueous layer. So what we did, like ammonia can dissolve in both aqueous and alkaline solution. Organic solvent. So we have water and we have trichloromethane. Trichloromethane is CHCl3. That's also a solvent, liquid. Ammonia can be present in trichloromethane. Ammonia can also be present in water, both of them. So what we did, first we took a 75 cm cube and 4 mole per dm cube aqueous ammonia solution. Like the ammonia, originally all ammonia was dissolved. So we have the concentration. Original concentration was 4 and the original volume is 75 cm cube. Then we add 75 cm cube of a trichloromethane. Like this 75 cm cube of a trichloromethane is also added. means the total volume become 150. The two liquids are allowed to separate. So we allow the two liquid to separate. Like some ammonia will be there in water. Originally, all the ammonia was there in water, aqueous. But some ammonia dissolve in trichloromethane as well. Now, we separate the two layers and we take only the aqueous layer or the one with water. And from this water layer, which was 75 cm cube, we only take out 25 cm cube. So we took out 25 cm cube and we titrate. So this 20 out of 75, we took out 25 cm cube and we titrated with sorry. We titrated with HCl, hydrochloric acid. And the concentration of a hydrochloric acid was 4 and the volume of the hydrochloric acid was 24 cm cube, which was reacted with the aqueous ammonia of 25 cm cube. We have to calculate a number of moles of ammonia, like how many moles of ammonia, and then we have to calculate the concentration of ammonia in aqueous layer. How we can work out the moles of ammonia? Initially, because we have the concentration and the volume, like you can see 75 cm cube and 4 mole per dm cube. That was having all ammonia. So how to get the moles? Moles is concentration times the volume. So concentration is 4. And what about the volume? The volume is 75 divided by 100, 1000. What's the answer for this? $75 into 4 divided by 100. So 75 into 4, 300. So this will be 0.3. $75 divided by 1000 and times 4 to 0.3. So 0.3 are the original number of the moles, okay? That is the total number of the moles originally, initially. Now, then we will find how many moles are there in 25 cm cube. So first we'll find the moles of HCl. First we find the moles of HCl, and from moles of HCl we'll find the moles of ammonia. The ratio between them is 1:1. These are the total number of moles of ammonia which were used in the beginning of experiment. Then we are finding the moles of HCl. How to get the moles of HCl which are used for a reaction? So moles of HCl is concentration times the volume. Concentration is 4 and the volume of HCl is 24 divided by 1000 to get the moles of HCl. So we got 0.096 moles of HCl. How the mole ratio is 1:1? When you write a balance equation between the reaction of HCl and ammonia, the balance equation will produce ammonium chloride. That's why the mole ratio is 1:1. If there's a 1 mole of HCl, it needs 1 mole of ammonia. So if I have 0.096 moles of HCl, how many moles of ammonia will be there? X. So we got 0.096. So these are the moles of ammonia which are present in 25. So 25 cm cube contain this many moles of ammonia, 0.096. Is it clear till this point? Then how many moles will be there in 75? Because we only took out 25 and originally it was 75. So how many moles will be there? We'll just take a ratio. If 25 cm cube contains 0.096 moles, so 75 cm cube contain X. Cross multiply. So 0.096. So this will give us 0.288. These are the moles which are present in 75 cm cube, that is 0.0 0.288. And now to get the moles, to get the concentration of aqueous solution, we have the volume and we have the moles, so we can find the concentration. Concentration is moles divided by volume. So moles are 0.288 and the volume is 75, so 0.075. So when we divide, we'll get the concentration in aqueous solution, which is 3.84 moles per decimeter cube. Is it clear? So first we got the moles of HCl. From moles of HCl, we got the moles of ammonia in 25. From moles of ammonia in 25, we got the moles in 75. And moles in 75 and the volume, we divide them to get the concentration of ammonia in aqueous solution. Because the question was calculate the concentration in aqueous layer, and the aqueous layer was 75 cm cube. For a titration, we took only 25, but the total was 75. That's why we took a ratio that 25 contain this many moles, so 75 will be X. Is it clear?